Helium was first discovered because of dark lines observed in the continuous spectrum of light from the sun. These lines were caused by a few specific frequencies of light in the spectrum being present at a very much lower intensity than the rest. Scientists deduced that this was due to an unknown element in the sun's atmosphere, and then the question is asking us to explain how helium in the sun's atmosphere caused this dark set of lines for 5 marks. Right, so let's explain how absorption spectra are created. So here is a star. Inside that star you have a plasma, and a plasma is basically a soup of protons, neutrons, electrons, and nuclei. And these protons, neutrons, electrons, and nuclei, they're all smashing into each other at very high velocities. The plasma of a star is incredibly hot. Atoms do not stably form within the plasma, so electrons do not bind to nuclei. If they were to bind to nuclei, they would very quickly be kicked off because of high energy collisions knocking those electrons out of the atom. And this plasma creates a continuous spectrum of light. Continuous spectrum basically means that all of the different frequencies of light are present. The intensity of those frequencies will vary to some degree, but you do not see dark lines that are at a very much lower intensity than the rest. So this continuous spectrum that's created from this plasma travels out towards the exterior layers of the star, and here it meets the photosphere. And the photosphere is basically a cooler layer of the star. I say cooler, it's still very hot. So the surface of our star, the surface of our sun, has a temperature of around 6,000 Kelvin. But the photosphere is cool enough for atoms to form. So you can have electrons stably being bound to nuclei. And it's these atoms within the photosphere that are absorbing some of the frequencies of this radiation that's being emitted by the plasma. And that's what causes these dark lines. Alright, so let's refer to this diagram over here to go over that in a bit more detail. So this is part B of the question. We're not answering part B just yet, but we're going to use this energy level diagram to explain this concept. Let's look at the difference between two energy levels in this diagram. So n is equal to 2, n is equal to 1. The difference between these two levels is 1.9 eV. So what that means is, if you have a photon that has an energy equal to 1.9 eV, then that photon can be absorbed by an electron in the n is equal to 1 state. So if we have an electron over here, that photon can be absorbed by that electron, and the electron can then jump from n is equal to 1 to this next energy level in the atom, and that photon no longer exists. And then because these photons are being absorbed by the atom, they will then have a lower intensity in the spectrum of the star. Now there are many different transitions or excitations that are possible, and each individual element has a different set of energy levels. So each individual element, these numbers are different for them, and therefore there are a unique set of energy level differences for each individual type of element. And therefore certain energy photons can be absorbed, and because the energy of a photon is E is equal to hf, that means that certain frequencies are absorbed, a certain set of frequencies are absorbed for each individual element. And the frequencies that are absorbed are characteristic to that element. So hydrogen might absorb 4 particular frequencies of visible light, helium might absorb another 10 or something, and those frequencies, those set of frequencies will be unique to each individual element. So what does this look like overall? If we were to look at an absorption spectrum, what does it actually look like? So here on the right hand side is a picture of an absorption spectrum of a star. We see a pretty much continuous spectrum, but with a bunch of these dark lines at various places within the star. Again, these dark lines correspond to photons of specific energies that are being absorbed by atoms inside the photosphere, and each element is responsible for a set of these different lines. So it could be the case that hydrogen is causing these particular frequencies to be absorbed, and then helium is causing another bunch of frequencies to be absorbed. And if we see all of those lines present in that absorption spectrum, then we know that the element that is responsible for those lines must exist within the photosphere of the star. Okay, so how can we summarize this for 5 marks? First point I mentioned, the atoms of a star reside in discrete energy levels, and photons which have energies equal to the difference between energy levels in atoms are absorbed. So just going back to the diagram, a photon that has an energy equal to the difference between these two levels, so a 1.9 eV photon, can be absorbed. Third point, the atom then excites, electrons go up an energy level. Fourth point, the energy level differences that we have, so the differences between these levels, are unique to each individual atom, or unique to each individual element. And then the final point, E is equal to HF, so that's the energy of a photon. So if the energy level differences are unique to each atom, that means that only photons of specific energies are absorbed, so specific frequencies are therefore absorbed, and that lowers those frequencies' intensity. And for part B, the diagram shows some of the energy levels for an atom of another element. Determine which energy levels are associated with photons of frequency 4.6 times 10 to the 14. Right, so first thing we need to do is work out the energy of these photons. So use the equation E is equal to HF with this frequency that we have over here. So Planck's constant multiplied by this frequency, and that gives us 3.05 times 10 to the minus 19 joules. Next thing we want to do is to convert this to EV. So 1 EV, 1 electron volt, is equal to 1.6 times 10 to the minus 19 joules. So to work out how many electron volts are in this amount of energy, we would divide this by what 1 EV is in joules. So we do the 3.05, 10 to the minus 19, that's the total energy that we have for this photon, divide it by the energy in joules of one single EV, and that gives us how many electron volts we have. So that is 1.9 to 2 sig figs. And then we look back at our energy level diagram, and we see which of these transitions has a difference of 1.9 eV. Well, we discussed this in part A. It's the difference between n equals 2 and n is equal to 1. The difference between these two is 1.9 eV, and therefore the energy levels which are associated with photons of that frequency are 2 and 1. And there's two processes that you can discuss here. So the first process is the one that we covered, that's excitation, when an electron in the n is equal to 1 state absorbs a photon of 1.9 eV and then jumps up to level 2. The second scenario is when an electron within the n is equal to 2 state de-excites, drops down from n is equal to 2 to n is equal to 1, and it emits a photon which has an energy equal to 1.9 eV. And in the final part, B part 2, suggest why the energy levels all have a negative value. Okay, so let's look at our energy level diagram. So, if an electron in one of these states receives just enough energy to become free from the atom, then that free state is defined to have 0 eV of energy. So let's say that this is the just free state from the atom. That's defined to have 0 eV of energy. That's the n is equal to infinity state. And this energy of 0 eV is comprised of two parts, kinetic energy and potential energy. The kinetic energy of the electron is 0. So if you have an electron in the n is equal to 1 state, we supply it with just enough energy to leave the atom. It has no kinetic energy left over afterwards. All of its energy was used to leave the electrostatic attractive forces of that atom. So it has no kinetic energy in the n is equal to infinity state. The second part of that energy is potential energy, and this is where there's some subjectivity. Potential energy is a relative quantity. We can define it to be 0 wherever we want it to be. And it so happens that an electron, which is just free of the electrostatic attractive forces of the atom, is defined to have a potential energy of 0. So if this is your atom, and then we have an electron which is a significant distance away from that atom, this electron will not experience an attractive force from that atom. And when it's at that point, when it experiences no attractive force, no electrostatic attractive force from that atom, then it's defined to have 0 eV of potential energy. Okay, so our just free of the atom state has 0 potential and 0 kinetic energy. And all of these other states are then relative to this energy that we have over here, to this just free state. So let's go into that in a bit more detail. So if we have an electron in the n is equal to 1 state, that electron requires a certain amount of energy to become just free of the atom. And that energy happens to be 3.41 eV in this example. So if this electron requires 3.41 eV of energy to get to 0 eV of energy, then that means that this energy level state must have had minus 3.41 eV of energy to begin with. So if you're adding a certain amount of energy to this electron in this state, if you're adding 3.41 eV to get to 0, that means we must have started at minus 3.41 eV of energy. And that's what all of these numbers mean. This is the deficit of energy, the amount of energy that we need to get to that 0 eV, to get to that just free state. Alright, so how do we summarize this for 2 marks? First mark, electrons with 0 kinetic energy that are just free of the atom are defined to have 0 energy. That's the first thing we'd say. And if electrons in bound states require energy to get to that just free state, so this electron here requires energy to get to that just free state, then it must have started with a negative energy to begin with.